Okay. All right, good. So I see the recording sign. All right, so let's start. Okay, so today what we're going to do is we're going to start in where we were last time with looking at the equation of lines, and then we actually put things into vector equations. So let me just review a little bit beforehand. All right, so we're looking at the two-dimensional case. And there are three things that can happen when we have lines. So first of all, if we have two lines, let's say L1 and L2, they can give us a unique solution. Okay. And then another situation is when the two lines actually coincide. So here's L1 over here. Let me see if my color works. Of course, we use red and black, right? So here's the other line L2. Okay. So they actually coincide. And in that case, we have infinitely many solutions. Oh, sorry. Can you speak up, please? I can answer your question. Go ahead, Lucy. Oh, okay. I guess we don't. Okay, so we have infinitely many solutions when, when the two lines coincide. We saw that case. And then finally, the last case is if the lines are parallel. Okay, so they have the same slope, but they have different like y-intercept, then there's no solution. All right, so those are the three cases. And last time what we did was we sort of looked at an example of the first case, and then we actually put this in the context of looking at vector equations. So let me call this case 1, case 2, and case 3 here. Okay. All right. So let's revisit case 1, and then we'll go on to case 2. So here's the example. So x plus y is equal to 10, and 2x plus y is equal to 6. All right. And what we did was we actually put this in terms of a vector equation by pulling the x out and then pulling the y out. So we have x and 1, 2. And then we pull the y out and we get the vector. What vector do we get? Anyone out there?
1 and 1.
Excellent. Very good. And that's equal to 10, 6. Okay. So geometrically, what's going on is we're able to take, let's see, the vector 1, 2. So the one vector 1, 2 looks like this. Let's call this V1. And let's call this vector V2. And the other vector looks like this, V2. And we're able to actually get the vector V3 by stretching these two. Let me clean this up a little bit. It looks a little sloppy. So here's the vector here, and this is the vector V1 here, there. So we're able to get the vector V3 here by stretching V1 by X and V2 by Y, and then we obtain the vector V3. And we actually found what X and Y were. Okay. Now, what we can do is we can continue on. And let's look at another case. So we have X plus Y is 10, and 2X plus 2Y is equal to 20. Okay, so this is line L1 and this is line L2 there. Okay, so notice that L1 and L2 are the same line, right? I can divide by 2 on L2 and just get L1, right? They have the same slope, same y-intercept, so they have to be the same line, okay? So the line L1 is actually equal to L2 in that case. Now, let's apply the same vector procedure that we've done to the prior example. So we'll pull the X out and we'll pull the Y out and see what we get. So what do we have? We have X times 1, 2 plus Y times 1, 2 is equal to 10, 20. Okay. And then we can combine these two. So X plus Y times 1, 2 is going to be equal to the vector 10, 20. All right, so let's call this quantity T. All right, so notice that if I take T, I can make T be equal to 10. All right, and then I get a solution. All right, so T equals 10, we get a solution. And then that means that X plus Y has to be 10. Okay, so there are infinitely many points, X and Y, which satisfy this equation, right? So because we can only have to stretch in one direction, then we get infinitely many solutions. Okay, good. And then finally, let's look at the example we had in the last class. What's it? Oh yeah, here it is. X plus Y is going to be equal to 10. And X plus Y is equal to 20. Okay, so here we have two lines, and they both have the same slope, but they have different y-intercepts. Okay, so we're basically in case 3 over here. Okay, and let's try to do the same thing with the vector equations this time, right? So I take X, and I have 1, 1 plus Y times 1, 1 is equal to 10, 20. Okay, so I combine the X and the Y again by just adding this, and I have 1, 1, and that's equal to 10, 20. All right, now let's again call this T. So I have a question to throw out at you guys. So if I stretch the vector 1, 1, can I ever get the point 10, 20?
No.
Right, so there's no T. Excellent, so there's no T that works. Hence, there's no solution. Yeah, so from these examples, I hope that you can actually see that we can reinterpret systems of equations actually using vectors and the idea of stretching vectors and seeing if a vector, I'm going to use this word, which I'm going to define later on, is actually in the span of those vectors. So we can actually generate the vector like 10, 20 as a combination of the vectors that we had before. And that turns out to be equivalent. Well, we'll see this later on. Okay, so I just want to make one definition. So here's a definition. system of equations is called singular. Okay, so that's the word. If and only if the system has no, so it means the system has no solutions or infinitely many solutions. All right, so we could look at these cases again and note that in case one, we only have one solution, right? In case two, we have infinitely many solutions. In case three, we have no solution. So from this, we can sort of deduce that cases 2 and 3 are singular. So cases 2 and 3 are singular. And case 1 is not singular. Okay, so are there any questions up until this point?
Yeah, is there a term for not singular?
Well, sometimes that's a good question. So sometimes the term non-singular is used. Okay, so well, we're not going to use this term too much, but you may see it in the literature. So that's why I wanted to point it out. So you see it in your book, and so I just want to clarify this. Okay, other questions? Great. Okay, so we're going to change gears a little bit. So now I'm going to start in on the promised algorithm, the be all to end all in this class. So you'll get lots of practice with this. And so this is called Gaussian elimination. All right. So so the idea is I have a system of equations that I want to solve or find the solutions of. So this algorithm will actually be able to tell you whether a system of equations is singular and not singular. And moreover, you'll be able to get or obtain the solution for the system of equations. Okay, so I think the best way to do this is just start on an example, and then I'll just kind of run through it, and I think you'll just get the hang of it. I mean, it's not super hard, but you know, you just have to make sure you don't make mistakes. Okay, so I mean, it's not computationally, you just have to, you know, be very careful. A long time ago, you know, when I was taking undergraduate linear algebra, I was in a class of like 300 people. And the professor was up there and then did Gaussian elimination. And then at one point, the professor made a mistake. About half the class knew where the person made the mistake and unfortunately didn't tell the professor. And at the end, you know, of course, the answer didn't come out correctly. So this algorithm is very, very sensitive to making a mistake at a certain point. If you make it earlier, then the mistake will actually replicate and make more mistakes. So I'm just saying, just kind of be careful when you actually calculate it. Okay, so here we go. So let me start with the system of equations. So 2x plus y plus z is equal to 1. Okay, so that's one equation. And then 4x plus y is going to be equal to minus 2. Okay, that's another equation. And finally, 2x plus 2y plus z is going to be equal to 7. All right. So how many equations are there? Anyone?
3.
Okay, so 3 equations. And how many unknowns?
3.
Okay. So basically I have 3 planes. You know, I have plane defined by the first equation, a plane defined by the second equation, and a plane defined by the third equation. And I want to see how these things intersect. And we know that, you know, there could be a variety of choices or outcomes that actually could happen when we have planes intersecting in 3-dimensional space. Okay, so what's the idea? So the idea is to first put this in a matrix form. Okay, so that's the first thing you actually want to do. And I'll show you how to do that in a second. And the second thing you do after this is you want to transform your matrix over here to something which looks upper triangular. So with zeros down here. Okay, so you want a matrix which actually has like entries above the diagonal in some sense. Okay, and then there could be other stuff over here. Okay. And then finally, once you have the equation in the nice form, involving the upper triangular form, you do a back substitution. So then you do what's called back substitution. And then to solve. Okay, so let me go through these procedures. So the first thing is to do is you take your coefficients. So the variables sort of come along for free. You just have to make sure that, you know, you put things in the correct columns so that your variables are kind of represented that way. But we don't have to drag around the X, Y, and Z, right? So I'm just going to put the first line up here, 2, 1, 1, 1. Okay, and I'm going to put a line, and the book doesn't do this, but I think you should, is to actually put a line where the equal signs are, because it does matter where the variables are and where the actual part outside the equal signs is. Okay, so the next thing is, you know, you just follow along this. So what's the next row? It's 4, 1, 0, minus 2. Okay, and minus 2, 2, 1, and a 7. Okay, so does everyone see how we got the matrix? Good. All right, now the next thing to do is to use what are called pivots. So what I want to do is I want to actually put zeros places. So the way I'm going to do this is I'm going to take one equation, I'm going to multiply it times a number, a non-zero number. I'm going to add it to another equation, and I'm going to replace that equation. Okay, so we'll do this sort of in steps. So let me just circle this thing. So this 2 is called a pivot. Okay, so I'm going to use it to knock out the 4 and the minus 2. Okay, so here's how we do that. Okay, so the idea is I'm gonna knock out the 4. So in order to knock out the 4, I have to multiply 2 by minus 2. Okay, so I'm going to multiply it by minus 2. So the idea is I'm going to take minus 2 times equation 1 plus equation 2, and I'm going to put that into the second row. Okay, so that's the first thing I'm gonna do, all right? So let's do that. So I have 2, 1, 1 here. I have a 1. All right, so -2 times 2 plus 4, that's gonna be a 0. And then -2 times 1 plus 1 is equal to what? So I'm taking this one and then I'm taking the second one, I'm adding it to that over here. I get -1, right? And then the third one is -2 times 1 plus 0, I get a -2. And then finally I get -2 minus 2. I add those together, that's -4. Okay. Does everyone see how we do this? So we use the pivot to our advantage. And we multiply the pivot times something so that we can knock out the thing underneath the pivot. Okay? All right, so now I want to knock out the -2 also. So let's do that. So I'm going to knock out the -2 over here. So I'm going to multiply times 1. So I'm going to take equation 1 plus equation 3, and I'm going to put it in the third row. Okay? So I'm just going to add equations 1 and 3 and then put it in the third row. So I get 0 here. What's the next term? Anyone? What do I put in next?
3.
3, good. Next one,
2.
2, good. Next one,
8.
8. Very good. Okay, so notice that after I completed this, using the pivot, I was able to get zeros below the pivot. Okay. Now, now I want to put it in upper triangular form, so I want to get rid of the 3. So now I'm going to use, change colors again. I'm going to use this one as a pivot. Okay. And I'm going to knock out the 3, as you can imagine, by multiplying the second row times 3, adding it to the third row and putting it in the third row. Okay, so it's very, very nice and easy. Okay, so I put the multiplier out here just to kind of keep track in my mind what I'm doing. So I'll just write it out. So 3 times equation 2 plus equation 3, and I'm going to put this in the third row. Okay. So now let's go down and do that. So I get 2, 1, 1. I have a 1, 0, -2, -2, -4. And then I get 0, 0. Okay, so 3 times -2 plus 2 is -4. Okay. And 3 times -4 plus 8 is also a -4. Okay. Now, when we do this procedure, it turns out that the system of equations is the same. All right, so it turns out that this equation up here is the same as the equation that we have here. So let me put a star here for this system of equations. And this system of equations is 2x plus y plus z is equal to 1, and minus y minus 2z is equal to -4, and -4z is equal to 4. So let me call the star star, and we know that star and double star are basically the same. or give the same set of solutions?
Sorry,
Sorry, question?
Yes, the last equation is minus 4z equals -4, right?
Yeah. Oh, -4. Thank you. Good catch. Thank you very much. You guys aren't as cruel as that, my class that I mentioned before, a long time ago. Okay, good. So if you catch any mistakes, please let me know. All right, great. So now these two equations are the same. Now notice that the equation here at the top compared to the equation down at the bottom. Well, which one is better to solve or easier to solve?
The one on the bottom.
Yeah, the one on the bottom, because what I could do is I can now back substitute. I can sort of solve for z. And then once I solve for z, I can solve for y. Once I solve for y and z, I can solve for x. Okay, so maybe the internet on my end got disconnected or something. Okay, so we're back now to a situation where we have to back substitute. All right, so we have -4z is equal to -4. So z is going to be equal to 1. Right, so that's one thing we know automatically. So we've used this equation over here so far. And so now what we do is we go back to the equation above this. So we have -4y minus 2z is going to be equal to -4. Okay, so now we know z equals 1, so we plug it in. So minus y, okay, -2 is equal to -4. Okay, so that means -y is going to be equal to -2. And so now y is equal to 2. All right, so we have z and y, and now we go up to the third equation. Okay, so we use the second equation. Now we're going to use the third equation. And now we have 2x plus y plus z is equal to 1. And now I'm going to plug these in. Okay, so we have 2x and y is 2, z is 1, and that's equal to 1. And now I have 2x, let's say plus 3 is equal to 1, 2x is equal to -2, and x is equal to what? -1. Okay, so we started with this system of equations. We had no idea whether or what the solutions were, whether it was singular or non-singular. And then we used this algorithm systematically to put it in a triangular form and then back substitute, and we get the solution. All right, so here there's a unique solution. And the solution, I'm just going to write out x, y, and z is going to be equal to, let's make it look nice, -1, 2, and 1. Okay, so this is non-singular, if you want to think of it that way. So this is non-singular. Good. All right, are there any questions on this? We're going to do lots and lots of examples. So, if you don't catch everything the first time, we're just going to repeat the process. Go ahead. Sterlane is raising her hand.
How do you choose the pivot? Like, is the goal just to make one of the variables have all zeros?
So the
Like,
goal is you start with the system of equations. And basically you want to put it in this upper triangular form. Because with the upper triangular form, it's easier to solve. And so once you have it in this upper triangular form, you can use back substitution and just solve for, your solution. Does that answer your question? I hope that's more clear.
No, but how do you know which ones to pick as pivots? Because in the
So-
beginning, you could have chose
Yeah,
negative
so,
2 as a
okay,
pivot.
so this is a very good question. So what you do is you do it systematically. So I want to turn this into sort of an upper triangular form. So you sort of want to start with the first column. And then use the first column and knock out everything underneath the pivot in the northwest corner. Okay. And then once you're done with that, you want to move to the second column, right? And then knock out the entry sort of in the second row, using the thing in the second row and everything underneath that entry, like what I have here. And then once you're done with that, you move to the third row, a third column, and then you sort of keep going with the procedure. Okay, so you kind of do it from left to right. Is that more clear?
Yeah, that makes sense.
Well, we're going to do another example in a second. Okay, this is not the last time you'll see this. Okay. Okay, other questions? All right. Great. So let's do another example. Okay, so another example. So suppose I have the system of equations y plus z is equal to 20, and x plus y plus z is equal to 15, and 3x plus y plus 2z is going to be equal to 10. Okay. So let's apply the procedure. So first of all, I'm going to put this in a matrix form. So I got 0, 1, 1, 20. Okay. And 1, 1, 1, 15. And 3, 1, 2, 10. Okay. So let's start trying to knock things out, right? So what do I have here? I have a 0. Now, can I multiply anything times 0 to knock out the 1?
No.
No. So we're sort of stuck here. We're in a little trouble, right? So can anyone think about a way to get around this?
Just like go the opposite direction.
Okay, that's
Upside
one
down.
way. That's actually one way to do that. And then someone said in the chat, switch places of the rows. And that's exactly right. So what we can do is we can just switch the rows, and it doesn't change the system of equations, right? So in this case, switch rows. Okay, so let's put the second row at the top. So I'm just going to move this to the top. So 1, 1, 1, 15, okay? And I'm going to move the second row up, so 3, 1, or third row up, like this. And since I have a 0 already, I won't have to do much work if I just kind of put it, in either the second or third row. So let's just do that. Okay, so this system of equations is the same as the one that we started with. So we just switched the order of the equations. Okay, so now we're in good shape, because now what we can do is we can use this thing here as a pivot. Okay. So let's now just apply the procedure again. Okay, so what do I want to do? I want to multiply the first row by what?
-3.
Good. So -3. So I'll just be very explicit here. -3 equation 1 plus equation 2. I'm going to put in the second row. Okay, so I keep the first row the same. Going a little faster now. It's 0. -3 times 1 plus 1 is -2. -3 times 1 plus 2 is -1. Okay, -3 times 15 minus 45 plus 10 is going to be what? Oh, we could just do this one. Minus, so it's going to be minus 45, this is minus 35. Okay. And then finally, I can just keep the third row the same because I already have a 0 down here. Okay. And then you just proceed on as before. Now, if I want to make things a little bit nicer, it's better to have like a 1 as a pivot. So I could actually switch the second and third rows if I want. So now you just proceed as before. Yeah, can't spell today. Okay, so you just proceed, you finish off the problem by putting in a triangular form and then back substitute. Okay. So now I'm going to start with another example, and then some other things can happen. Sorry, there's a dog. Don't worry, the dog is okay. Okay, so let me start with another example. So x plus 2y plus 7z is actually equal to 0, and minus 2x minus 3y plus 9z is going to be equal to 4, and minus 2y plus 10z is equal to minus 8. Okay, so I have a system of equations like this, and so I actually should be careful because this is a minus here. Okay, so let me just make sure is correct in my notes. Okay. All right, so now what I want to do is I want to apply the Gaussian elimination algorithm again. So let's set this up. So again, the procedure is the same. 1, 2, minus 7, 0, minus 2, minus 3, 9, and a 4 here, and a 0, minus 2, 10, and minus 8. Okay, so I'm going to I'm going to use this as a pivot here, and I'm going to multiply the first row by minus 2. So 2 times equation 1 plus equation 2. I'm going to put it in the second row. Okay, so 1, 2, minus 7, 0. And I get a 0 here. And what I get minus 1. The next one is minus 14 plus 9. It's minus 5. And 0 times 4 plus 4 is 4. Okay. And then I have a 0, minus 2, 10, minus 8. Okay, is everyone with me so far? We're just doing the same thing as what we did in the first example.
I have a question.
Yeah.
Is the -1 in the middle row supposed to be a 1 or?
It is supposed to be a 1. Thank you again.
Thank
Like I
you.
said, we have to be very careful. Okay, let's recheck this. 0, 1, minus 14 plus 9 is minus 5, 4. Okay, very good. You guys are following along very well. Okay, anything else? Okay, good. Let's keep on going. So I want to multiply now this one by 2, right? So 2 times equation 2 plus equation 3. I'm going to put it into the third row. Okay, so 1, 2, minus 7, 0, 0, 1, minus 5, 4. And then I get 0, 0. What's the next term? Anyone?
0,
0. And the last one is
0.
0. Okay. So now you look at this and you say to yourself, well, what's going on here? All right. What does this mean? So what's the solution set going to look like?
Is it infinitely many?
It will be infinitely many because basically I've reduced the 3 planes down to an equation involving just 2 planes. So like you notice, I'm just taking like the intersection of 2 planes, which is going to be a line, and I'm going to have infinitely many solutions. Good. So this algorithm could sort of tell you if there are infinitely many solutions or not. And now what I want to do is I want to substitute. So here's a pivot, and presumably here's a pivot too. So in order to back substitute, you make the non-pivot columns into what are called free variables. So make non-pivot columns into the free variables. So I'm going to make z, which is not a pivot column, equal to t, and this is a free variable. And then you back substitute. Okay, so that's what I'm going to do. So let's do that. So our equation is y minus 5 times t is equal to 4. Okay, so that's using this equation here. So what do we get? I want to solve for y. So y is going to be equal to 5t plus 4. Okay. So we have this, and we have that. And then the last one is x plus 2y minus 7z is 0. So x plus 2, and I'm going to substitute the y in 5t plus 4 minus 7 times t is 0. Okay, so that means that x plus 10t plus 8 minus 7t is equal to 0. So when you do all this out, so I should get minus 3t. Okay, so that's right, and minus 8. Okay, so you just do some simplification, you get this. All right, so I have x, y, and z, and so I can write this out in a nice way. So x is going to be equal to minus 3t minus 8. You just put that in, 5t plus 4, and finally z is equal to t. And then you pull the t out, so you have t minus 3, 5, and 1. So t can be anything you want. And then you have 8, 4, and a 0. Okay. All right, so this is our solution set where T is any number, any real number. All right, so what does the solution set look like? Anyone? So geometrically, if I'm looking at 3 space, what I do is I take this vector V here, I can stretch it in any direction, and then I shift it up to 8, 4. So let's say this is the vector W over here. And then I just shift this line up to this place up here. Okay, so it's an equation of a line. Okay, so this is what we get. We get the equation of a line. So there are infinitely many solutions. So by back substituting, you can actually get solutions in this parametric form where you can actually see like how many free variables you have and what dimension your solution set's going to have very conveniently. So instead of getting just one solution, you could get infinitely many solutions. And there are also cases where you get no solutions too. And so what we'll do next class is to actually look at a case where we have no solutions on Monday. Okay, and we'll actually work with this Gaussian elimination algorithm a little bit more and become a little more fluid with it. And you'll see that you can solve lots and lots of problems with this. Okay, so let's see, I guess it's 8:12 now. So thank you again for your time and patience. And we will look forward to seeing you on Monday. Are there any questions? Yes, no? Okay, so I'll stop the recording and then I'll try to post the recording today and also the notes. Okay, so see everyone on Monday.
Thank you.
Thank you.
Bye-bye.
Thank you.
Welcome.